So, so guys, shall we begin? So we are here to hear hear a talk of Sanchita Paul, who is visiting us from India. She is a graduate student of Dibyendo Nandi at IISER in Kolkata. But she did her master in radio physics in space science in University of Kolkata in 2015, and right now she is on her way through the graduate school. She also received a COSTEP visiting scholarship in 2017 and she was hosted by Gopal Swami at NASA Goddard Space Flight Center. And her main interests are CMEs both near Sun and near Earth, and their magnetic and kinematic properties. And I think this is what you're going to be talking about right now. So,
yeah. Thanks, Anna, for introducing me. Thank you for giving me this opportunity to talk about my research in HAO colloquium. So I'll be talking on the topic that the erosion of coronal mass ejections due to magnetic reconnection with the ambient interplanetary magnetic field. So coronal mass ejections are the sporadic ejection of plasma, which can erupt with a velocity range from 100 km per second to 3000 km per second and with huge energy. So they are observed in coronagraphs such a bright structure which are formed due to the Thomson scattering of the energetic particles coming out along with it. So they can put some coronal, so they can leave some coronal signature when they erupt from the sun. So like flare brightening. So if the CME is accompanied by flare, then at the source region some bright structure one can see. So that is called the flare brightening. And another signature one can see, that is like post eruption arcade. So they are formed due to the reconnection at the foot point of the overlying flux tube. And another thing, another signature might one can see, that is the coronal dimming. So this dimming is mainly generated due to the displacement of flux during the eruption of CME. So these all one can see in UV image of sun. So here whatever image I have shown here, all are taken from SDO-HMI. So so CMEs can erupt in three-part structure. So that is the leading edge, which is generated due to the shock of the CME, and the cavity, which is the second thing, and which is mainly the flux rope of CME, flux rope part, and next is the core, which is the prominence of filament material of CME, of the source region of the CME. So when the CME comes out from the sun, then it carries the solar magnetic field along with it, and when it reaches it to Earth, as Earth has magnetic field, and so it can reconnect with Earth's magnetic field on a favorable condition, and then the energetic particle can enter through the magnetic reconnection to the Earth's polar region. So it can create beautiful aurora structure at the polar region, and also it can create geomagnetic storms, and such storms are such storms can affect the aviation system and the GPS system and other power subsystems. So so I will tell a little bit about the eruption cause of the CME. So one of the cause might be the ideal instability. So when the CME flux ropes, so due to the photospheric motion of the CME's flux rope foot points, so then what happens? So the flux ropes get sheared, and due to its sheared and twisted and kink, due to its twisted structure, so it's when the twist reaches to a certain kink level or threshold, then the pressure difference increases, and then it is susceptible to erupt. And so here I have shown one picture of UV image, which is showing the twist structure of the flux rope, and this is this is at the coronagraph by MLSO, which is showing again the entangled structure of the flux rope, and this is the one twisted flux rope simulated by Torok and Clem in 2010 paper. So and another reason might be the magnetic reconnection. So the magnetic reconnection provide the amount, means a huge amount of energy to the CME flux rope to get erupted. So it might the magnetic reconnection can happen, as I told already, that to the foot points of the overlying flux rope, and then at this point, and reconnection will provide a huge amount of energy to the flux rope, and this will help the flux rope to erupt. And another reason, scenario might be the break, like when the flux rope erupts in a plasma, like plasma blob, like a plasma blob, then it will reconnect with the nearby magnetic field and the overlying field as well. So then the huge amount of energy it will get to erupt from its source region. So when the CME maintains its flux rope characteristics during its propagation through the interplanetary magnetic field, even when it reaches to the earth, then it is called the magnetic clouds. So here I have shown one schematic of magnetic cloud, which is perpendicular to the sun earth plane, and this is the schematic of magnetic cloud which is parallel to the sun earth plane. So the magnetic cloud axis is along this direction, and this is the magnetic field, the magnetic cloud's azimuthal magnetic field. This is the spacecraft where this is the region where the spacecraft is sitting. And so one can observe the magnetic cloud at 1 AU by in situ observation. So some signatures we have to see whether the signatures are there in the solar wind, then we will confirm that there is magnetic cloud. So the signatures are like magnetic field strength will increase, and the second one is the magnetic field rotates smoothly during the magnetic cloud duration, and the proton temperature will decrease during that time, as well as the plasma beta will decrease. So this is one this is the solar wind parameters. Like this is the magnetic field intensity, the magnetic field vectors, and this is the rotation angle of the magnetic field, like this one is I think velocity of solar wind, and the lower one is the proton density, and next one is the temperature of proton, and next one is the plasma beta. So so these vertical lines are showing the interval when the magnetic cloud was present in the solar wind parameters. So you can see that the magnetic field intensity increases from the normal ambient value, and the magnetic field has smooth rotation. Like this red one is defining the y field, that is the azimuthal field. So this has rotation from north to south, from south to north, and the blue one is the BZ of the magnetic field. So it was completely southward. I think it has caused the geomagnetic storm too. And these are the magnetic field rotation angle. This is theta and this is phi. And next one is the solar wind speed during the magnetic cloud speed. So you can see the magnetic cloud is gradually decreasing, means the magnetic cloud is expanding, and this is the proton density. So you can as the magnetic cloud is expanding, so the proton density at this region is also decreasing, and the proton temperature which is also lesser than the ambient temperature, which is shown by this dotted line. And next is the plasma beta. So as it is a flux rope, so it is very common that plasma beta should be less than 1, because the gas pressure there is lesser than the magnetic field pressure. So by this we identify the magnetic cloud is present in the solar wind. So when the magnetic cloud propagates through the heliosphere, due to the presence of the ambient interplanetary magnetic field, the interplanetary magnetic field will wrap the magnetic wrap around the magnetic clouds, and if the direction of this wrapped magnetic field is just opposite to the magnetic cloud's magnetic field, then it will erode the magnetic cloud. So here this is the cross section of a magnetic cloud, and you can see the azimuthal flux, azimuthal fields. These are pointed by this arrow, and this is the ambient fields. So when they come closer, in this you can see that they have reconnected, and so the part of the magnetic cloud's magnetic field is eroded. So that can be observed at 1 AU by this structure. Like this blue line is the azimuthal field variation, and this red line is the accumulated flux. So accumulated flux has been the accumulated flux are the flux which is calculated at the plane which is formed by the magnetic cloud axis, which is coming out from the plane of the surface of this thing, and the plane of the spacecraft trajectory. So that plane, in that plane we will consider that the gradient of B will be equal to 0. So it means that if the flux rope is not eroded, then there should not be any variation in this red curve, means the accumulated azimuthal flux. But the flux, if the flux rope is eroded, then this the imbalance of this red line will be seen. So you can see that due to the erosion at the front of the magnetic cloud, so sorry, at the back of the magnetic cloud, so it will be at the back, yeah. So the imbalance you can see at the front of the magnetic cloud. So when the magnetic cloud will be eroded at front, the imbalance can be seen at the back, and it will be otherwise for the other case. So yeah, so these magnetic clouds erosion have some important effect on its geoeffectiveness. So Labrador et al. 2014 has explained it by some model. So they have modeled one magnetic cloud using Lundquist model, like constant alpha force free model, and they have plotted the so they have modeled one magnetic cloud with considering a particular magnetic field intensity and particular velocity of the magnetic cloud, and they plotted they figured out the electric field of the magnetic cloud, and as there is a strong correlation between the electric field and the DST index. The DST index is the storm index, which depends on the encircling ring current of the earth. So as the electric field decreases gradually due to the erosion, then the DST index will also decrease. So and this is the change of the DST index with time. So this black this black the black line which is showing the electric field of the magnetic cloud when it is not eroded. So that black line corresponds to the black line of the DST index here. You can see that for this the DST index was maximum. It is the maximum intensity was around like minus 147, and when it is eroded maximally, like when this red line is representing the electric field of the eroded magnetic cloud, so for that you can see the DST index is very small, and the change of DST index is also very small. So they performed this analysis and found that around 30% of the magnetic cloud, means around 30% of the geomagnetic storm can decrease due to this erosion of the magnetic cloud. So it is very important to study that how this erosion is happening and on what this erosion actually depends. I will show here some of the important results which have been found till now on the analysis of magnetic cloud erosion. So mainly the magnetic cloud, the eroded magnetic cloud is observed as a flux rope, which is followed by an extended coherent magnetic region, which is shown here. So this black thin line is showing the By component, like the azimuthal component of magnetic field, and this is the accumulated flux. So you can see the front and rear boundary of the magnetic cloud is observed following the procedure which I have explained just now in the last slide. And so this this orange color bar is representing the imbalance of the accumulated flux. So this amount of flux is eroded of this magnetic cloud due to the reconnection. And another important result is that magnetic cloud may be eroded at front as well as rear. So when the so front erosion is pretty much clear because the CMEs because if the magnetic cloud has a greater velocity, then it will create a shock ahead of it, and then due to the compression of the interplanetary magnetic field, then the erosion may happen at the front of the MC. But at the back of the MC, similar thing might happen because the first solar winds which are coming from the coronal holes and the correlating interaction regions, when they hit the magnetic cloud from behind, then the magnetic then there might appear some compression of the magnetic interplanetary magnetic field, which will actually erode the means which might reconnect with the magnetic cloud from behind. So another important result is the reconnection rate for the reconnection exhaust at 1AU, which several study has found that is pretty much lower than the observed than it should be for the observed eroded flux amount. Because so I will try to explain it. Because several studies have found like the reconnection rate, but this reconnection rate at 1AU means if the reconnection is happening at 1AU, they found the reconnection rate is very small, like 0.02, like that. But if but as from the analysis of this eroded flux, so from this analysis it is found that the reconnection rate is pretty much high, like 0.12 kind of. So for some events people have studied it, and it has been found that the reconnection rate is pretty much higher than the reconnection rate which is calculated at 1AU reconnection. So it means that reconnection is happening not at 1AU, it is happening in the inner heliosphere, or in the middle region between the sun and the earth. And the next thing is, as we know that reconnection rate is proportional to the like it scales with the Alfvén speed, and the Alfvén speed does scale with the magnetic field intensity. So it is very sure that as the magnetic field intensity is higher near the sun, so there should be the higher rate of reconnection. And even so this is this is the thing which we know from the theory, but in observation also 2 or 3 events has been analyzed by people the scientists like Dasho and Rafnak. So they have found like 54 hours before the magnetic cloud has been eroded when it reaches to the earth. So it means, and another study by Lavrod, they have found like they calculated the accumulated Alfvén speed, and they found that the accumulated Alfvén speed will increase at the heliocentric distance about 0.3 AU, which means that as it is the Mercury's orbit, so which means that means they showed like 47 to 67% of the erosion is happening at already started before, and it's happening at like 0.3 AU. So it means that it's happening before it reaches to the earth, like to 1 AU, and it is pretty much before. And so another important result is that people have tried to find the eroded flux relation with the 1AU local solar wind parameters, like its Alfvén speed and like observed Alfvén speed and change of Alfvén speed, but they could not find any correlation between these two, which is another evidence of the fact that the erosion is not happening at 1AU, it is happening far before 1AU. So it is very important to find the dependency of magnetic cloud erosion, means on what factor it actually depends. So as I have told that when the magnetic cloud propagates, then the interplanetary field wraps around it, and so we can so this is interesting to see that whether the magnetic cloud erosion depends on the intensity of the interplanetary magnetic field or not. So for this we will try to find any relation between this IMF intensity and magnetic cloud erosion or the eroded flux. So we know that IMFs are the large scale magnetic field lines which are originating from the coronal holes, and the Ulysses spacecraft observation showed that this IMF does not have the radial magnetic field intensity of IMF does not have any variation, latitude longitudinal variation all over the heliosphere. So so one can calculate the IMF intensity at any heliocentric distance using the open flux of sun. So if we know the open flux of sun, and if we know the particular distance at where we are trying to find the intensity of BR, then we can do it easily by using this equation. So people have studied this before also, and they found that the in situ observation at 1AU of this IMF intensity and the IMF intensity which is derived from the open flux, it has a it has a nice correlation like 0.68 kind of. So so as IMF BR has a direct correlation with the open flux, so we will concentrate on finding the dependency of magnetic cloud erosion on the open flux, not like we will take it as a proxy of the IMF intensity. So we calculate the open flux using the radial magnetic field intensity at 2.5 RS, that is the source surface, coronal source surface. So we calculate the flux using PFSS, a potential field source surface extrapolation, which considers that the magnetic field that the coronal magnetic fields are force free, which maintains the curl of B equal to 0 equation. And the input, and the input to this PFSS is the photospheric magnetogram. And so here we okay, so and here I have shown the synoptic magnetogram of a photosphere, so which is in -10 to 10 Gauss saturation level. So within this, and so and it is taken from the HMI magnetogram, and using this we have done the PFSS analysis at 2.5 RS. We can see that these red lines are the positive open field lines, blue are the negative line open field lines, and these black are the closed field lines. So we will calculate the magnetic open magnetic flux of CME of the sun using this radial magnetic field information. So this part of the work has been done by my colleague Shomoranjan Das. So, and I am doing the full CME part. So now I will come to my work. So that is, now we have selected 72 magnetic clouds from solar cycle 23 and 24 during the time interval 1998 to 2018, and following the criteria which I have already described. So you can see here I have shown one magnetic cloud along with the angle lambda. So the lambda angle has a very importance in finding this erosion of the magnetic cloud. So this lambda angle is actually the angle between the magnetic cloud axis and the spacecraft plane, which is perpendicular to the ecliptic plane. So this is the you can take the spacecraft the magnetic cloud axis, this line, and this line is the spacecraft plane, which is perpendicular to the ecliptic plane. So this is the lambda angle. So if this lambda angle increases, then the magnetic cloud erosion will be falsely detected. So I will show here. So so here we can see the magnetic clouds are represented by one magnetic cloud is represented by this red line, and this red farm line is showing the magnetic cloud axis, and this A, B, C, D are the various spacecraft path. So for the spacecraft path A, the lambda angle is minimum because the spacecraft is passing almost perpendicular to the axis of the magnetic cloud, and for that you can see the accumulated azimuthal flux is this one. So this one is there is no imbalance in this accumulated flux if the magnetic cloud is not eroded. But if you observe this D spacecraft line, which for which the lambda is maximum, so for that you can see here the imbalance is generated, although the CME is not eroded. So it can so this is important to take that lambda to consider the lambda angle. So already studies have found that if the lambda angle is less than 45 degree, then the magnetic cloud azimuthal flux imbalance will be less than 10%. So for all the events we have considered here, the lambda is less than equal to 45 degrees, which is maintaining this criteria. So the next thing is to convert the coordinate of the magnetic cloud. So a magnetic cloud which are observed at 1 AU, those are in GSE coordinate system, and we have to convert it to a common coordinate system, that is the cloud coordinate. So you can see the GSE coordinate describes the x GSE will be towards the sun, and the z will be the perpendicular to the ecliptic plane, and y will complete the right hand triad. And if the magnetic cloud axis is defined by this blue arrow, then then lambda will be this angle which I have already told you, the angle between the axis and the perpendicular to the sun earth plane, and this theta and phi describes the latitude and longitude angle of the magnetic cloud axis. So magnetic cloud when the magnetic cloud arrive at earth, so it can make several different theta and phi angles. So so it's little bit complex if we don't consider a common cloud coordinate, like which will be like this. If it is the cross section of the magnetic cloud, then z cloud will be through the magnetic cloud axis, and x cloud will be through the spacecraft path, and y cloud will complete the right-handed right-handed triad. So it means that whatever direction the magnetic cloud can have, then we convert it to this coordinate system, then it will be easy to analyze the magnetic clouds eroded flux. So it can be, so conversion from this coordinate to this coordinate can be done using this theta and phi. So we have to derive this theta and phi of the magnetic cloud. So that can be derived using two methods. One is the minimum variance analysis and another is the flux flow fitting to magnetic cloud. So minimum variance analysis will not be using, because these methods have several, means different result for different angle of theta and different impact factor. So the impact factor is the distance between the spacecraft path and the magnetic cloud axis. So for this method, if the distance between these 2 points increases, the method result will be very bad. Like we cannot take the result of that of the theta and phi using this method. So that's why we choose to go with this flux flow fitting method. So also we have some this method also has some discrepancies, but these discrepancies are consistent for all the events, irrespective of their impact factor, irrespective of their theta and phi. So that's why we chose to go with this flux flow fitting method. So we did a flux flow fitting method to magnetic cloud axis to get the orientation of magnetic cloud. So we fit the magnetic cloud with a constant alpha force free model, that is curl of B equal to alpha B in cylindrical coordinate, and this model is based on the fact that the error that ERMS should be lesser. ERMS is the RMS error between the observed field, that is BO, and the model field BM. So the model will start with some initial values, and it will go till when it will get the ERMS value minimum. So minimum ERMS value, when it will reach, then it will stop to model the magnetic cloud. So this is the result of the magnetic cloud modeling. So this black line is the real data, and this red one is the model data. And so we found this using this flux flow fit model. We found the theta and phi of this magnetic cloud as these values. So next we will come to the direct method. So using this theta and phi information, we will implement it to a method that which is called direct method. So it is called direct because it is directly we calculate the magnetic cloud flux from the observed values. So it is based on the fact that gradient of B will be equal to 0 at the plane formed by X cloud and the Z cloud. And so the flux will be the azimuthal flux is this one. So this will be the integration of the by cloud component along the spacecraft axis, around the spacecraft path, and which can be written in this way. So here I will show you two example of the magnetic cloud erosion calculation. So this first one is a magnetic cloud whose By cloud is shown by this blue line, and this red one is the accumulated flux. So you can see that the shaded region, for both of them, the shaded region is showing the accumulated flux which was in the magnetic cloud before it get eroded with this interplanetary magnetic field. So you can see the imbalance is sitting right up there. So it means that as imbalance is created, it means the magnetic cloud is being eroded. So for this, the erosion has occurred at the front. That's why the imbalance is generated at the back, and for this event the erosion has occurred at back. That's why the imbalance has occurred at the front. So this red circle is showing the eroded azimuthal flux. So which is so the values are kind of this. So so we have applied this thing to the 72 events which we have found, and finally we will show you the results. So first we have first I will show the distribution of this eroded azimuthal flux. So for this analysis we have we have considered the normalized eroded flux, not the actual eroded flux. So the normalized eroded flux is the eroded flux which is over the total azimuthal flux. Now, so you can see the distribution of this flux is shown in this plot. So if the negative values are showing the flux which are the magnetic clouds which are eroded at front, and the positive values are showing the eroded at back. So you can see that out of 72, we have found like 40 magnetic clouds are eroded at front with the value this, with the eroded flux value this, and the 32 eroded at back with eroded value of 23%. It means that it suggests that the magnetic cloud is eroded. It suggests that the magnetic cloud is eroded both front and rear in similar proportion. This result has been found by other people also, so we did it just to confirm our result. And the next result is this. So here this distribution is showing you the eroded magnetic flux distribution, magnetic clouds flux distribution is irrespective of the of its position, where you can see all are positive values. So during solar cycle 23, we found that the flux eroded flux was around 28%, which is greater than the eroded flux, which is around 22% at solar cycle 24. So now we will introduce the effect of the open flux of the sun's open flux to the eroded flux. So so this is so I'll explain it. So the first plot is showing the dotted black lines are showing that showing the open flux average value in each year, and the red line are showing the magnetic clouds eroded flux average over in each year. So you can see it is almost following the dashed line, which is the open flux, and the errors are shown in this with this vertical bar. And we have found that the correlation coefficient, linear correlation coefficient is at 0.58 with like around 99% confidence level. And here we have plotted it in scatter plot and fitted and did a regression analysis and found this linear fit with coefficient 0.66. It means that the normalized eroded magnetic cloud flux and the open flux has almost a linear relationship, which is actually expected, because as I have told that the reconnection rate has a good correlation with the like reconnection rate depends on the Alfvén speed, and Alfvén speed depends on the magnetic field intensity. So as the reconnection rate determines the reconnected amount of flux, so there should have the reconnected the good correlation between the reconnected flux and the magnetic field intensity, IMF intensity. So here IMF intensity we have not considered, as I have mentioned earlier. We have taken the phi open as a proxy of IMF intensity. So the conclusion of this thing is, one is that the effectiveness of reconnection at magnetic cloud boundaries has significant correlation, positive correlation with the open flux. And another one is, as I in the last slide I have means just previous slide I have shown that that in solar cycle 23 the amount of eroded flux is greater than 24, which is actually following the open flux amount also. So in solar cycle 23 the open flux was greater than the average open flux was greater than the average open flux of solar cycle 24. So now I will little bit discuss our result. So first I will tell that we considered open flux instead of IMF intensity because it is really difficult to identify where the heliocentric, in which heliocentric distance the erosion is has been started. So people have different different opinion, like someone has done with some single event and they told that 54 hours before it has been started. Some people have done on, like I have told, like it is around 0.3 AU it is been started. So it is not clear. So that's why we have not gone to that controversy, and we have taken only the open flux as the R like heliocentric distance effect is not there. And the second one is the flux row fitting method, which we have considered there. So that fitting method takes that axisymmetric of geometry, because all the time we consider the expansion of flux row, but but all the time the flux row will be symmetric from its center. So which does not happen when one CME get eroded. So then it is not the symmetric thing. So that's why always we will get the result, whatever result we will get, that is like that is a consistently lower value we will get. So as we are doing for a huge data, like for a 2 solar cycle data, so we have that will not affect in our result, because for all of the data the effect will be same. And next is the normalized eroded flux of magnetic cloud is overestimated for high impact factor value. So I told you that if the impact factor value is high, then the eroded flux will be overestimated. It means that if the normalized value of eroded flux, because the normalized value is equal to the actual eroded flux value over the total eroded flux, total azimuthal flux value. So if the impact factor is high, the total azimuthal flux will be lower. So it means that the normalized eroded flux will be a little bit overestimated. And finally, that consider here the whatever the asymmetry is generated due to the erosion, which is not the fact. Sometimes it happens that the CME magnetic cloud is propagating, and just behind that one filament materials are there which can protrude through it, and which can break its structure, and then sideway transport of the magnetic cloud azimuthal flux may happen, and thus asymmetry may generate. So if we consider all these things, then we think that our result will be little bit upgraded, or it will be little bit good. But again, if we consider these things, then our data set will be decreased. Already for 22 years we got like only 72 magnetic clouds after our selection criteria. So we think that if we consider this, then the magnetic cloud event will be more, the number of events will be more decreased. So I would like to acknowledge my department, which is Center of Excellence in Space Science India, and I would like to acknowledge the help of Dr. Benoit Labrot, who has helped me with his discussions. And I'd like to thank Dr. Katsuhide Maruasi for providing his constant alpha force free model to me, and also Dr. Anthony Eads for for making the open source of the PFSS model. Thank you.
Questions?
Just maybe I might have missed this in your presentation, but how do you determine what part of the fluxrope you're looking at?
What part?
Like you had an angle, right, from your spacecraft. How do you determine that angle? It was gamma?
Oh, that angle we feed the model, constant alpha force free model, and we find the theta and phi angle.
Questions? I actually have a question.
Yeah.
In your last slide with the discussions, you mentioned that the non-axis symmetrical CMEs would affect your measurements, but when you do a big data set statistics, those uncertainties would even up. Can you explain that a little more?
Okay.
Why would they even up?
Okay, so the thing is that the model which we are using, that model will fail, not fail, that model will give you, can give you erroneous answer if it is non-axis symmetric structure. But the thing is that for the effect of this non-axis symmetric structure will be same for all of the events, all of the eroded flux events. So that's why we can ignore that, because we know that there is error, but that error is implemented for all of the events, then we can ignore that error. So did I address your question? Right?
Yeah.
Okay. Thank you.
Okay, Sarah?
Yeah.
So I wonder if you could explain a little more about the protruding filaments and how it results in the asymmetry of all of that.
So so as I have read from papers like Manchester et al. 2014, so they did one simulation on this. So they did what they did. They explained that when the protruding filaments have twisted structure. So for this twisted structure, they will carry they have the pressure difference in them. So for that, they will they will put aside, they will create kind of shock, not shock, they will put a huge velocity, means come with a huge velocity through the magnetic cloud, and then due to the pressure difference it will cut the magnetic clouds component. Mainly it cuts the azimuthal field components like that. So then yeah.
What is the major implication of this study? What does this erosion do to
Okay, Yeah, so what happened that if you don't consider the erosion and if you try to predict the magnetic clouds geo-effectiveness, then you can get like you have not considered the erosion. So so you can get a huge amount of DST index, but which is not might happen because due to the erosion it can lose some of its magnetic clouds, as I told in this field that in this slide. Just 1 minute. Yeah. So here, see, for a non-eroded magnetic cloud, the black line, this black line for a non-eroded magnetic cloud, the DST index is pretty much high, and for eroded magnetic cloud, the DST index is very low. So it means if we don't consider the erosion of magnetic cloud, then we can miss this part.
Next speaker again.
Thank you.